Okay, it seems to be working. And let me share it with you. Great. And let me see if I can go back to where we were. Yeah, this is not your class. That may be going back too far, not sure. Okay, this is what I did in office hours. And I'm not sure if I did this in office hours as well, perhaps. I think so. So let me talk about this and talk about the sample test and get rolling here. So what do you say? Is the people who were there, was this something I did in office hours? I believe it is. I guess it's not too, it doesn't take too long to do regardless. It's probably a good thing to recap. So I supposed we had a Markov chain that had these transition. These are one-step transitions. And the state space is 0, 1, 2, 3, and 4, as you can see. And we had just talked about communication being an equivalence relation. And in equivalence relations, you have what are called equivalence classes. So it's all, so for example, 0 would be all the states that communicate with 0, all the states I and S that communicate with 0. Well, if you look at this picture, 0 communicates with itself because you can go, well, that's automatic, that's the reflexive property. But it also communicates with 1 and 2. There's a path going from 0 to 2 with positive probability and a path back, and the same for 0 and 1. So these 3 states communicate with each other, and that's what so they're in the same equivalence class. However, the state 3 only communicates with 4. It doesn't communicate with any of these 3 states because basically you can get from any of these 3 states to 3, but you can't get from 3 back to them. So the only states that 3 communicate with is 3 and 4. So this is how the equivalence classes look in general. Equivalence classes partition the Venn diagram of state spaces into disjoint sets. That's a general result from equivalence classes. And in this case, the state space is 0 through 4. So it splits up the state space into 2 sets, one set that looks like 0, 1, and 2, which is this one, and the other which looks just like 3 and 4, which is this. It turns out that states that are in the same equivalence class are either all recurrent, or all transient. So in this case, you can see what's going on. States 0, 1, and 2 are all transient. Why? The chance of going from any of these states back to itself eventually is not equal to 1. Why? Because there's a chance you leave and never get back, and that has a positive probability of happening. So these 3 states are all transient. On the other hand, these 2 states are recurrent because well, from one of them, there's really nowhere else to go except for the other and back and forth. Okay, so this was an illustration of a follow-up to what we did in class, how you can now look at the equivalence classes under communication, and that sort of groups similar states together. With that said, I said there'd be some future homework, which is problems 19 and 20. And I think, oh, I gave this example. You might think, oh, yeah, I think what I was saying here is something we'll say a little more soon. I was saying that for a finite state space, there's always a recurrent state. In this case, there are two, 3 and 4. But if you have only a finite number of states, then one of them at least has to be recurrent. And the reason for that is if they were all transient, then there would be sort of a last time you visit each of them. And that can't happen because you have to be somewhere. So, you can't be done visiting all the states and still have time on your hands here. So that's an intuitive argument. We'll see a more precise argument later. However, it doesn't hold if you have an infinite state space, and that was what I was saying here. If you have an infinite number of states, 3 dots, they keep going, and the chance of going up is always 1, then all states are transient because the chance of coming back to 0 is nothing. It can't be 1. It's certainly not 1. It's actually 0 because once you leave it, you never come back. And the chance of leaving is sure. By the way, that brings up an interesting case. So what I'm just saying, if the Markov chain looked like this, the probability of going from 0 back to 0 would be 0. Well, what's easier to see than 0? Well, I think they're both pretty easy to see. It's less than 1, and it actually equals 0. Why is it 0? Well, if you can get back to itself, you have to be able to do it for the first time in 1 step or 2 steps or something, but you can't even get back to yourself in any number of steps because you simply, on the first step, leave and never come back. So this shows, this shows that this is actually 0. Now, what I was going to say is really something a little different than that. Let me see if I can say it. Yeah, I guess I can't quite. Yeah, give me another 10 seconds, see if I can come up with what I wanted to say in that. No, I'll have to come back to it later because it doesn't quite follow. Okay. So this is what I did in office hour. If we flip the page, instead of doing it that way. I don't think I want to do that either. Okay. So that's back. I looked a little bit at problem 19. Did that in office hour as well. No, I did part of it. 19 gives you a transition matrix that looks like this. So this is from the book. This was the future homework. And I went from this matrix to this diagram. Basically, you were given 7 states that are 0 through 6. And these are the transition probabilities of going from one to another. And if you make a diagram from this, from the matrix, it looks like this. And all I wanted to do is analyze which, 19A, I guess here, asked which states are transient and which ones are recurrent. The one that was fairly clear is 0 is transient. Why? Whenever you, yeah, okay, that actually is the point I was trying to make in the other one. What's the chance that you actually go from 0 back to 0? So in this case, the chance of going from 0 back to 0 eventually, well, is just 1/2. Why? Because we've already done this kind of thing. This is the probability that the time it takes to hit 0 is finite, given that you start at 0. And we've already seen a way to calculate this. This would be the probability of first returning in 1 step, given you start at 0. Or, which means add, you first return to 0 in 2 steps, given that you started at 0. And keep going. You first return in 3 steps. First return to 0 in 3 steps, given that you started at 0, etc. That's how you can figure this out. And if you start at 0, the chance that you return in 1 step would be looping. So that would be this thing would be 1/2. But if you start at 0, the chance of first returning in 2 steps is 0. Because the only way to return is to loop, and then you've already done that in 1 step. So if you don't loop the first step, then you leave and you never come back. So all of these are 0 the rest of the way, and this is 1/2. And that gives you the answer of 1/2. And since it's less than 1, 0 is transient, which I labeled as such. Okay. Now, what about the other states? If you were to start at any of these states, for sure you're going to come back with probability 1, because if you start at 1, the chance of coming back in 3 steps is 1. And then the chance of coming back in 6 steps is 1. Why? Because there's a cycle going on here. There's nothing else that you can do. You have to go up by 1, go up by another 1, and then come back. So you can see the chance that you'll eventually get back to 1 is sure, it's certain. So that means 1 is transient. Whoops, that means 1 is recurrent. But from what we said, well, you can make the same argument for 2 and 3, or you can notice that these all communicate with each other, so they're in the same equivalence class. So if 1 is recurrent, then the others are recurrent. So I labeled them all as recurrent. Similarly here, once you end up in the states 4, 5, and 6, the chance of eventually going from 4 back to itself turns out to be 1 again, which means it's recurrent. And that's sort of the point I was trying to think up on the other slide. So I'm claiming that if you start at 4, the chance of getting back will will be 1. The chance of getting from 4 to 4 eventually will be 1. But I'm not going to say that's as obvious for 4 as it was for 1, 2, or 3. Because 1, 2, and 3, there were no loops, and you just for sure move to the next step. Here there are loops at all these states, and the chance of moving to the next step is only 1/2, not 1. So to actually verify that row 4, 4 is 1 from this kind of thing, or from definition, would be probably take a while. It might be complicated even. Another way to do it is to notice that once you're in these 3 states here, let me put a little box around them. Once you're in that, that's a little sub-Markov chain of itself. In other words, you never leave, you never get back to 0, and there's no way to get back to 1, 2, or 3. So this is like a little Markov chain itself. But I just said from the other slide that in any finite Markov chain, there's at least one recurrent state. So if we're using that, that would be an easier way to get this result. One of these states have to be recurrent. Suppose it's this one. Then they're all in the same recurrence class, and therefore they're all recurrent. And we'll go over some of this more today. So long story short, everything here is recurrent except for 0. 0 is transient because you leave it and never come back. Now, the point that I was thinking of making before, and I might as well make it here since I'm here. So I've just argued that this is 1. But somebody could say, well, maybe you go from 4 to here, and maybe you loop forever here. And that could happen, right? It's not very likely, but it could happen. And so if that happens, then what would you say? You would say you never get back to 4 because you go from 4 to 6 and you loop forever and you never get back. So someone can say, if it's possible never to get back, how could the probability that you get back be 1? So that seems contradictory. Maybe I've addressed this issue already, so I may be addressing it again, but let me do that because it is a little contradictory. It's sort of the case. We're saying something having probability 1 doesn't mean for sure it has to happen, even though probability 1 usually is translated into saying something happens 100% of the time. Well, let's see. So philosophically, what I said is true. You can go from 4 to 6 and loop forever. And if you do that, you'll never get back. But what's the probability of doing that? Well, if we're looping here forever, that would be like 1/4, 1/2 to the nth. And that's going to 0. Which means there's a way for you not to get back, but it has probability 0 of happening. Which means something could actually occur and not have positive probability. The chance of going from 4 to 6 and staying there forever. Philosophically, that could happen. I mean, you're just, how does the path look? It's pretty clear. You're going from 4 to 6 and it's staying at 6 all the time. So this could happen, but it's a little bit like flipping a fair coin and getting heads from some point on. That could happen, but what's the probability of it happening? The probability of getting heads from some point on is 0 because it's like 1/2 to the nth. So even though something can happen, it doesn't mean that the probability of it has to be positive, which is a little contradictory at first. Okay, I think that's all I did in office hours last time, but it's important to bring us all back on the same page. Any question on this example or the previous slide? Okay, so let me take a little time out and talk about the upcoming exam. I told you to look for it in the email, and I told you to look for it either Wednesday night or Thursday, and neither happened. Not because I forgot about it, but because I couldn't find it, good exam. So I sent you an exam, but I'm not entirely happy with it. Let me see if I can bring that up first of all. So I'd like to share that if I can. Let me go back to my email and see if I can. Yeah, here it is. Okay, so I can see it. Let me see if you can see it now. Yeah, that'll work. No, okay, so now let's see if I can share this. So I'll stop sharing and I'll reshare it. And there it is. Okay. So I assume you can see what I've sent you. This is page 1 of what I've sent you. I think it has 5 pages. My frustration is this. I taught the class in 2019, which is more recently than this. This was when 2018, it was still quarters. So I had 1 midterm and 1 final, and this was the only midterm. And that doesn't quite match where you're at because we're on semesters now. We have 2 midterms and 1 final. So I was spending a lot of time trying to find the 2019 exam, and I couldn't find it at home. I'm pretty sure I could find it if I go to school, but that's not an easy thing to do these days. So I kept trying to find it at home, and I came close. I found the 2019 second exam, but that's not appropriate for you because that's like the second half of the quarter then. So I came up with this one. Notice the class has a different number. It's now, in 2018, it was 4330. Now it's 4300. And it's not perfect, but I'm going with it. So this is typical. It says do any 4 problems. Maybe you could help me. How many problems were there on all 5 slides? Were there 6, I'm guessing? Has anyone looked them over?
Yeah, I think there were 6.
Yeah, I think
there's 6.
I think so as well. So that's 4 out of 6, which is fairly much what I promised you, that it'd be an open-ended test where you need to do 4. And if you have time, which I hope you will, you'll stay and do more than 4. And now I grade them all and add up your best 4, and that's your score. Okay, so this problem is fairly similar to what I was just talking about. Because the one we were just talking about had 6 states. And the one I was talking about was future homework number 19, which is now current homework, by the way. But this one, and that problem, you went from the matrix to the diagram. Here I just gave you the diagram, asked you to classify the states as transient or recurrent, and find some of these things. Now, some of these we haven't done yet, but now A and B, I think we should be able to approach. So, okay, even though I'm not happy that I have my most recent exam to share with you, I did find one that should fit. I don't think all topics on this have we covered yet. So let's just, you should start working on this test. It's a homework assignment, but it should be something you do even if I don't say that, because this is as near to the real test as you're going to get. Now, as I say, so far, there's a couple things here in C that I haven't even talked about. but I'll get to that before the test. So I would start doing whatever makes sense. So you can start doing A and B at least, and maybe even this part of C. The other part, either don't skip it for now, or if you're really curious, you can look in the book. Let me open another page and see how else it looks. So we're going to go back to my email. Here's the second page. Okay. And I'll just share it with you. Though you have your own version too. So I'll share this with you. Let's see, is that it? Yeah, that's it. Okay, so the second page of the sample test looks like this. I think you could all see it. And this is, well, the one-step transition matrix is given, the state space is given, an initial distribution is given, and it's asked to find pi 1, pi 2, pi 8. We've done that, so that's fair game. Asked to find this. Well, we're going to talk more about ways to do this. Find the joint distributions of these two and this. We've done that. So this problem should be something that you should be able to do. Maybe row 1, 2 is a work in progress. We're still working on things like that, but everything else here should be familiar. Let me go to the next page. This works as simply as I hope it does. Yeah, I can open up the next page. It describes, now let me see if I can share this with you. So page 3 describes some ways to mix balls from 2 containers. And you have to read this and then figure out how the diagram looks, and then find some 3, 4, 5 step transition probabilities. I think everything on here is something we've done again. Let me see if I can get rid of that. Yeah. So I think the hard part here is reading the description of how you're mixing the balls and translating that into the diagram. Once you have the diagram, all the rest should be stuff we've done. Okay. Let me just look at, there's only other 2 slides, so I might as well just make sure where we're at with both of them. So the fourth page looks like this, but I don't think you can see it yet. I'll stop sharing it, reshare, and there's page 4. Okay. State improved the Chapman-Kolmogorov equations. Okay, we stated and proved those. So this is probably one of the theorems I told the class to have memorized so that they would know how to do it. 4b, let this be the 2-state, find this. This is a homework problem. We did it in our class, they did it in their class. So this is, problem 4 is fair game. It's something we did in a homework problem. Number 5, we haven't got there yet, 5a. It's in the book. It's around where we are, page 15 or so. So we'll get there before our test, and that's the next order of business. But look at B. B looks like an infinite Markov chain. And I don't think the questions are here. I don't know what's under the toolbar here. I'm hoping it'll go away. Can you see what's under the toolbar? Is there anything there? Is it just the diagram? There's cleared. There's nothing except for the diagram. But the diagram goes on forever. because of the three dots here. So let me go to the last page then. So going back to the sample test. The last page of it is this. Okay, and let's make sure I can share this with you again. Okay, so 5B is asking that something is irreducible. With any luck, we'll get there today. Find this. We've done things like this. Show that the whole chain is recurrent. We haven't done that kind of thing, but this is not, we're not too far from it. Problem 6 is something we haven't done at all. These are called birth-death chains. They go on forever. And there are two types. Yeah, there's a tranche and a recurrent chain, and there's a way to decide which is each. But we haven't got there yet. So I would skip 6 for now. And of the first 5 problems, do as many of the ones that make sense to you. And we'll try to fill in the ones that we haven't got to later. Okay. Questions at all about the sample test? It's mostly appropriate. Let's see. It's a little, it's got some stuff we haven't done yet because we're at the end of the 4th week. And this was a test for the middle of the quarter. So it was probably the 5th week. So it's a little out in front of us. But our test isn't taking place this week or next week even. So this will be more and more appropriate as the days go by. Questions?
How long did you say that our tests were going to be?
Say it again.
How long do you say our tests were going to be?
Minimally, they're an extra hour. So we meet for an hour and 5 minutes. So the midterms would be at least 2 hours and 5 minutes.
Okay.
At least. And if you're all there and want a little more time, I'd probably give it to you. So try to schedule your day so you can take advantage of it. But at least, and I'm not saying you have to stay there 2 hours and 5 minutes, but that's the minimal time I'll allow you.
We don't have a date finalized for it, right?
No, and that's where we go. That's the next midterm. That's the next order of business, is to figure out when the test is going to be. So let me take this off the screen and go back to a blank screen. So I'll just do that. Let me go back to where we were. That works. Let me go to the next page. If that works, maybe I'll just see where I am. Well, I did this with the other class and it's appropriate for you, so I might as well use the same screen. Okay, where are we? We're at the 17th, not the 15th. I went over this discussion with my afternoon class, which is a graduate class. So we're not here anymore. We're here. This is a calendar, Monday, Wednesday, Friday, and this is September 17th. So that's the end of the 4th week. Next week is the 5th week. The week after that is the 6th. And so typically what I think I've been saying when people have asked is it's likely to be in the 6th week. But I have a difficulty with that, which I didn't realize. I have something that's going to take a lot of my time that's due on the 1st. And that means having to prepare an exam. And by the way, there are some students who are in both my classes, and I'm not going to force anybody to take both my tests the same day. So if you're in both my classes, let me know. And whenever, they may turn out to be different days, but if they turn out to be in the same day, I will make exceptions for those people who are in both my classes. There aren't too many. I think there's like 2 or 3 students of that description. Okay, so what I would normally have liked to have done is giving you the choice of the 6th week, either the 27th, the 29th, and the 1st. And even though, that would have been what, it would have given you, 10 days into the first possibility. That's we're here. And 12 and then 14 days to prepare, for any of these. But I'm not sure, but I'm suspecting you're going to prefer the first. If you prefer the first, I'm in trouble with the other thing that I have to do. So I was tentatively checking out to see what happened if I would actually go into the 7th week. This is week 7. And give you the chance, I guess it's what, October 1st, October 4th. Now let me see. Ricky, were you one that
Hello?
had conflict with risk class?
No, I do not.
You do not. Okay. And with Beecher, do you have a conflict with risk class?
No, the person who had a conflict with one of Risk's exams was in your later class, the 5110 class.
But they weren't in this class. Is that what you're telling me?
Correct.
Okay. Okay. So what I feel like giving you a choice of is the 27th, the 29th, or the 4th instead of the 1st, because I'm going to be super busy on the 1st and a little bit before. Is there any problem with giving you that choice?
I have a quick question.
Yeah.
At what point in these weeks will we have learned everything we need for the test?
Oh, you mean for this
Or for this midterm, yeah.
Looking at the sample test that we just went over, I would say you probably have 85% of what you need.
Mhm.
And definitely I'll be able to get, I'm suspecting, well, for sure you'll know it all by the 24th, but I think you'll know everything you really need by the 22nd.
Okay.
So that, there's the today and 2 more sessions. So yeah, I'd say there's two or 3 days, depending on how you view today now, as a place to go over everything you need. But I'm not gonna put stuff on the test that you haven't done. I've seen. Okay, so I think all of these dates are reasonable. I'm saying 27, even though it's sooner, but it's still 10 days away. And by that time, you will for sure have seen everything you need. So what I'd like you to do is decide which of these you want. And the only thing that's a little unusual is I'm skipping the 1st. Now, there's a possibility that you pick the 4th, and I think the other class was picking the 4th. And that if that happens, then I have the 2 or 3 people who have both classes, and I'll have to make special arrangements for them. But I will, if you end up with the 4th. So I'm asking you to pick one of these. This date, or this one. If it doesn't matter to you, don't vote, okay? Because it probably does matter to some other people. Okay, so let's make option 1 being September 27th. Option 2, September 29th. And option 3, October 4th. Okay, so with that said, let me get in a position where I can see. I'm not doing an official poll, I'm just going to count hands. I think that'll be good enough. So, okay. How many, naturally I've got someone with a lawnmower going right by, but hopefully you can still hear me. How many prefer the 27th of September? If you prefer that date, put your hands up. I've got 1, 2, 3, 4 that I see. Okay, so I'm just going to record that somewhere. So the 27th, I've got 4 people who want that. What about the 29th? If you prefer that date, could those who had their hands up before put them down, or I don't know if you could, can you do that?
Yeah, you can. There's a
Yeah.
button for it.
Yeah, I hope you, yeah, but I don't see people doing it. Let me give you another, I'll give you another few seconds. If you voted for the 27th, you should vote for one, right? Vote for your most favorite time. Okay. Millie, are you okay? Or it looks like you voted twice, but maybe.
Yeah, I want either the 27th or the 29th, if possible.
Oh, I see. You want to vote.
Yeah,
You want to
I
vote.
mean-
I see.
yeah. Is that illegal?
Well, I think it makes it a little confusing because I want to see which date you want most. Don't you have a preference between the two?
I don't have a preference for either or. It's just I'm hoping before the October dates for me.
Okay.
It would be easy, but
Yeah, I'm trying to think. I think I'm going to ask everyone just to vote for one date.
okay. Well, and then I picked the 20. Oh my God, that's hard. I guess I'll vote for the 29th as my friend.
Okay, so that puts it down to 3 for the 27th because you had voted for that. Yang,
Sorry.
same question. Did you vote for the 27th? I thought you had.
I think I voted for 29, right? Yeah,
Okay.
29.
Okay, so let's do this again, okay? Can everyone remove their hands? Okay, thank you. All right, so just vote for the one of the 3 dates that you want most, okay? Let's try it again. How many want the 27th the most? So now I've got 2. Okay. How many prefer the most the 29th? Okay, so now I've got 1, 2, 3, 4, 5 is what I see. I think it's pretty clear winner, but there could be abstentions here. As I told you, if you don't care, don't vote. Okay, so how many would prefer the 4th of October? Ah, that's a surprise. The 4th of October only has 1 hand. Okay. So it looks like the preference is the 29th. Am I correct? Because there were 5 for that, 2 for the 27th, and only 1 for the 4th. We're good. We're good. Okay. I think that's going to help the conflict. There won't be conflict with the other class. So thank you very much. There were a lot of people who didn't vote, so I guess it didn't matter to a good number of you, which is actually helpful. Should I read the chat? I usually don't. Heart attack. Oh no. Okay, that's it. This is why I don't read the chat. Okay.
Was the date for your other class the 1st or the 4th? Forgetting.
It was going for, people were going for the 4th.
Okay.
Because I wasn't allowing the 1st because of my conflict. Okay, so, all right, let me get back to the screen. We have a conclusion, we have liftoff, we have a date. Our date is the 29th, which is, this is our exam 1 date, which is 12 days away from today. And that sounds fine. Okay, so let's get back and do some math. If there's anyone here who knows a friend who wasn't here today, why don't you inform them that we actually came up with a date? And I'll remind you as we go along. Thank you. And that was an interesting vote. It didn't go the way I thought it would, which is just fine. So let me see if I can see where we are in terms of this. Yeah, okay. Okay, so here's a theorem which could help us in different ways. Um, I don't think I got to it. If I did, then please remind me, because I don't want to redo what I did, but I don't think I got to it last time. Suppose I is recurrent. And I leads to J. And these are what? They're both states in some Markov chain. These are states in Markov chain. So we're supposing that I is known to be recurrent. What does that mean? That means, well, actually, yeah, just to remind you, that means row I is 1. And I leads to J. Well, we have 2 ways to do that. In class, I said I leads to J means there exists a positive number, natural number, so that the probability of going from I to J in that amount of time is positive. So this is what this little arrow going from I to J means. And the vocabulary which we developed last time is that I leads to J. So if I is recurrent and I leads to J, the conclusion of this theorem is then J is recurrent. Did I state this last time? I don't think I had time, but if I did, let me know. I think we're doing something new. Excuse me. Okay, so some proofs I'll give a formal proof of, and some I'll just give an explanation. So this will not be a formal proof. I'll be content to do an explanation, which means I'm using intuition rather than a completely rigorous proof. So here's a way to think of this. Here's the, so I won't call it a proof, I'll call it an explanation. Sometimes I'll ask you to know the explanation instead of the proof, okay? So if we are at the state I, let's say this is the state. And let's say this is the time. So suppose at yeah, maybe it would be better to arrange it the other order. It's not a big deal. Let's put time first. And the state. So at time 0, we're assuming we're starting at I. Now, if I is recurrent, there will be a later time. I don't know when it will happen, but there will be some later time, call it time N1, when you return to I. So you can think of this as, at time 0, you're at I, and maybe this is the next time you're at I. So in between these times, you presumably would be somewhere other than I. Now, this thing continues in this manner. So there'll be some, let me put 3 dots here to show that time is passing by. There's some later time when you come back to I again as well. And the reason for that is rho I is 1. So when you hit I, the chance of coming back is certain, which means there'll be a later time that you're back at I. That's part of what the intuition is about recurrent states. So recurrent states are states that you come back infinitely often. So that's part of the intuition. Intuition are recurrent states. You return to infinitely often. And transient states, you only return to finitely often. So that's the way you should think of these states. Transient states we return to, or you return to. Only a finite number of times. Now, it could be a big finite number. I mean, you could return to the state 100 times, but then that 100th time, then you don't come back after that. So this is a good way to think of what the difference is between recurrent states and transient states. And remember, transient states have, well, I already said, this one has, the current one has rho I being 1. Transient states has rho I being less than 1. So if there's a probability that you don't return, that means you're there for the last time. Okay. Now, if I leads to J, that means there's a positive probability of getting from I to J. So we don't know how often it will happen, but we somewhere it'll happen, because if whenever we're at I, if there's a positive probability of getting to J, somewhere on this list, let's pretend the next time we're at I is in 3. I'm going to assume that maybe between these 2 times I was at J. Because, and again, this is an intuitive, this is hopefully an intuitive explanation, because if I was never at J, then I would be going from I, back to I, back to I, back to I forever, and I would never hit J. And that contradicts there being a positive probability of getting from I to J. So if someone says there's a 30% chance of getting from I to J, it doesn't mean it always happens when you're at I, but it would say 30% of the time when you're at I, you would get back to J. Okay. So maybe this is one of those times. Okay. But then what happens? So you're at J somewhere between 2 visits to I. But once you're at I, the times keep coming. what do we know? There's another time when you'll return to I. Call it N4. There's another time later on when you'll get back to I again. And what I'm saying is everything basically restarts here at this I. Hang on 1 second. We got a phone call that it's probably a solicitor, so I'll catch that later. Okay, what I'm saying is everything sort of restarts once you're at I. So the whole argument means eventually, I don't know where, maybe not at N6, maybe here, but maybe eventually down the line here, somewhere, let's say it happens at N7, I must have been at J before I returned to I. Because once I'm at I, the whole process restarts, and I know the chance of getting from I back to itself is certain, probability 1. And I know there's a positive probability along the way that I go from I to J. So that works here. There's a positive chance that I'll visit J. Okay, but look at this history, this history of where you are and what's happening. You're going to return to I infinitely often. And that makes sense because I is recurrent. But there will also be an infinite number of J's on this list. And that's because there's a positive chance of getting from I to J. That's because of this hypothesis here. So if there's going to be an infinite number of J's on the list, that means the chance of going from J to J is certain, or that means you're going to be visiting J infinitely often, which is the conclusion. So there will be an infinite number of visits to J. This implies that J is, the chance of going from J to J is 1, because you're always coming back. You're going to have an infinite number of them. Now, there may be a lot more visits of I in between, but who cares? You're coming back to J infinitely often, which means that J, so what does this say? It says J is also recurrent. Which is the conclusion of the theorem. Okay. Does the explanation make some sense? Just to repeat it, because I is recurrent, you'll be visiting I an infinite number of times. Among those infinite number of visits of I, there will be an infinite number of visits to J, which means that J is also recurrent. Why? Because we think of something that's not recurrent as having only a finite number of times that you visit that state. Okay, this is the intuitive explanation. There's a more precise proof, which I'll tell you about, so you can read it. Oh, actually, I'm glad I looked it up, because the theorem is a little more than what I meant. There's a little more to it. Suppose I is recurrent. Okay, so where is the theorem? It's theorem 2 on page 21. So take a look on page 21. And this theorem actually is theorem 2. And let's correct it or complete it. They got it in terms of X and Y, and I have it in terms of I and J, but that's the same thing. Let I be a recurrent state, and suppose I leads to J, then J is recurrent. Okay, and so there's a little more to it. Rho ij equals rho ji equals 1. Okay, so my explanation got us to here. What about this part of it? Well, we're saying that if you can get from, if I is recurrent and it leads to a state J, then the probability of eventually getting from I to J is equal to 1. Notice that the probability of getting from I to J, well, how many visits are there going from I to J? There's an infinite number of them. So that's essentially saying eventually this will occur. And it's saying the opposite will occur. But I think the intuitive explanation I gave is a little more convincing for the first half of this. So you would probably want to read this. Read the proof. Where is the proof? It's on the bottom of page 21. And see if it makes sense to you. We can talk about it next time. Last thing I'll say, I'm really out of time, is a definition. And I'm trying to see where it is. There it is. So on page 23, it says a closed set of states is called irreducible if X leads to Y for all choices of X and Y in C. Okay. So yeah, I don't like that definition as much as I could. So let's see, I can specialize that. Maybe an easier way for me would be the following. Suppose we have a Markov chain. With only one equivalence class. So what does it mean? The states are these again. So this is the state space. So you can think of the Venn diagram constructed with the state space. When we're talking about communication, that partitions the state space into disjoint classes. Maybe it looks like class 1, class 2, class 3, class 4. In these classes, if you're in the same class, that means what? So if I and J are in the same class, that means I communicates with J, which means I leads to J and J leads to I. if the state space is such that there's only one big equivalence class, so the whole state space is not divided into 4 places like this, it just has one, that would mean that any state, any 2 states communicate with each other because there's only one equivalence class. And what does that mean? That would mean for all I and j in the state space, I communicates with j, which means I leads to j and j leads to I. If that condition holds, we say the state space is irreducible. So, for example, something that looks like this. The arrows are the one-step transition probabilities. So if you can get from any state to, well, you can get from 0 to 1 in 1 step. You can't get from 0 to 2 in 1 step because there's no arrow that goes directly there. From 0, you either go back to 0 or you go up to 1, but you don't go to 2. But it's clear that, you know, if these are all the states, I think it's clear that I communicates with j, no matter what I and j you pick. So if you pick 0 and 1, it's clear that 0 leads to 1, you can get there in 1 step. And it's clear that 1 leads to 0, you can get there in 1 step. And if you want to pick 0 and 2, you can get from 0 to 2 in 2 steps. So that means 0 leads to 2. And similarly, 2 leads to 0 because you can get from here to here in 2 steps. So if no matter where you are, you can get somewhere else in the state space, then we say the state space is irreducible. So here, this is the state space and it's an irreducible one because this holds for every I and j in the state space. So anything that, if you have more than one equivalence class, then it's not irreducible. Okay, so we can go, by the way, you can go from the partition to creating a Markov chain. So suppose I had a state space that goes like 0, and then I have like 1 and 2 communicate with each other. I'll make it 1 and 3, and then maybe 2 and 5, and 2 and 4. Suppose these were the equivalence classes. Could you construct a Markov chain that does this? Yeah, because 1 and 2 are in the same equivalence class. So that means you must be able to go from 1 and 3 rather, 1 to 3 and 3 to 1. So let's just write down all the different states and see what this could mean in terms of the diagram. Okay, so if I'm at 1, it leads to j, and then if I'm at j, it leads to 1, but I and j don't lead to any of the other states. So one way to do that would be something simple like this. 1 and 3, if you're at 1, you can go there and then go here. I didn't want to go to 2 to 3 because then there may be more in here than just 1 and 3. If I want 2 and 4, I better add a state 4. So maybe the simplest example of this would be this, and then this would be another one. And 0 could look like this. Okay, so if that's how the diagram looks, you can see that 1 leads to 3 and 3 leads to 1. And therefore they communicate, therefore they're in the same equivalence class. Same with 2 leads to 4 and 4 leads to 2. So they communicate with each other, so they're in the same equivalence class. It's not the same as this one, because if these were in the same, then that would say 2 and 3 communicate with each other, and they don't. There's no way to get from 3 to 2 or 2 to 3. And the only other class is 0, which is just looping on itself. So this could go with this, but what else could the diagram look like? Does it have to look like this? Not quite. There are other possibilities, so let me just list the other possibilities. Let's start with what I have here. I'm just redrawing what I had. We could have this situation, but maybe 0 goes to 1 as well. What does that make this? That makes this state transient, and still the equivalence classes would look like this. The only thing that communicates with 0 is itself. 0 can go to itself. 0 can go to 1, but there's no way to go from 1 to 0. So that means 0 and 1 do not communicate with each other, which means they're in different classes. So this also has the same kind of decomposition of the state space as we had before, but this time we have a transient state. Could we do something like that again? Sure. So we could have this one again, 2, 3, 4. Let's put down where we began. We began with something looking like this and looking like that, and having transitions this way. And this is where we began. And now we put this arrow in. What would happen if we also put an arrow that goes from here to here? I guess I could have just gone 0 to 2 as well. No matter. Okay, if you look at this diagram, the decomposition into equivalent classes is still the same. Why? The only thing that communicates with 0 is 0. 1 and 3 still communicate with each other. You can go from 1 to 3 and 3 to 1. 2 and 4 still communicate with each other. But now there's a way to go from here into this. That's all there is. And all of these would have the same decomposition as this. Now, what more would I want to say on that? Well, for each of these cases, what are the states recurrent or transient? This would be recurrent. These both would be recurrent. These would also be recurrent. I don't want to go into why. I will right in office hours, but I'm just trying to show you that all of these diagrams lead you to the same kind of decomposition of the state space. This one has this one being transient. And then these are still recurrent. If you don't know why, ask me in the office hour. I'll go into it in more detail. What about this one? Well, this one is still transient, but now these are both transient. And these are both recurrent. So even though the decomposition of the state space is the same, whether these classes are transient or recurrent can change by the addition of these arrows. And this is not the end of the game. There's a lot more of these, and I guess I lost this one. Okay. Let me see if I got enough for you to do homework. I already said you got the sample tests, so you should start working that. And I said earlier, you should be able to do some of 19 and 20. This is also more homework. 19 and 20, but I don't think you can do it all. So let me, 19A I already did. Trying to see. Yeah, I think you could try to do B. Okay. So do 19A and B. And 20A. B is more questionable. B's for sure. Did I tell you to do 17 before? I'm not sure. But you should be able to do that too. Okay, good place to stop. So I'm going to transition to our usual office hour. Any questions before doing that? Cool. So I'll see, for those who can hang around, I'll see you shortly. And for those who can't, have a good weekend. I think I've given you all enough to do. And we have a midterm date, so cool. Let me drink a little something, then I'll be right back. Is it windy wherever you are?
No, but it is getting cooler a little bit. I can tell.
Yeah, no, that's welcome. I'm looking at the clouds outside my window. They look like the kind of clouds that come when there's a little wind up there. But I don't see the trees swaying. Okay. So let me take a request. I will look at any homework problems. Even the sample tests, though I think it would probably be better if you try those first. I might be more interested in doing some of these or some of the ones that preceded that. I'm also happy to go over any explanations. Or proofs. I really didn't do a full out proof today, but I did ask you to look at one of them.
So really quickly, those different Markov diagrams we made,
Right.
none of them were irreducible, correct?
No, that, I mean,
Okay.
yes, you're correct.
Yeah,
None of them are irreducible because to be irreducible, there'd just be one big class and everything would communicate with everything else.
okay.
And that's my way of phrasing what they're calling irreducible.
And then really quickly, to go back to that theorem we were going over earlier, where if I was recurrent, then J was recurrent.
Right.
So I understand your intuitive explanation from going from I to J.
Okay.
And I guess my way I was thinking of to explain from J to I, couldn't you say that, like, you kind of just have to like switch your frame of reference, I think.
Yeah.
Because
Yeah,
if-
you can say, I think what you're going to say is, suppose you start somewhere on this ladder at some J, and then for sure you're going to hit I.
right. Because we're saying that from going from I eventually back to I, we're going to hit J.
Right.
So then if we just say we'll eventually hit J, then because we're eventually going back to I, then
It all happened again and again. Yeah.
right. Okay.
Yep. You got the idea. You got the intuition. Good. So this is a pretty nice result. It's telling you Now, if we take a step back from the explanation, it's telling you that if you're at a recurrent state, any recurrent state, and it leads to anywhere else, where it leads to is another recurrent state. And the chance of getting to there or coming from that state back to the other is 1. So this is giving you a real nice tool for figuring out rho under different situations, as opposed to what? Our other tool, what would be our other tool for doing this? Our other tool for getting rho ij would be the definition. What's the probability that the time it takes to hit j is finite, given that you started where at I? That's our definition of what rho ij means. The chance of going from I to j eventually. And then we've done this where you just write out tj is 1, tj is 2. And sometimes that's easy to get a number from, and sometimes that leads to a series that you don't know how to sum. So this is sort of giving us another way to find rows where we don't have to go back to the definition. The more ways you know how to do something, the better prepared you are to handle different problems that can come your way. And along with this one is this other one that I said earlier. If you have a finite chain, there must be at least one recurrent state. Because if there were not one recurrent state, each state would be transient, and that would mean that you, after a finite amount of time, you'd leave that state forever. So if there were 5 states, if you leave 0 forever after so much time, you leave 1 forever after so much time, and you leave 2 forever after so much time, and so forth up to state 4, then each state you're only at a finite number of times. Then the question would be, where are you after that time has passed? And the answer comes back, you have to be at one of those states. There's nowhere else to go if there are 5 states. So that means they can't all be transient. If they were all transient, that means after a certain finite amount of time has elapsed, you would have nowhere to go. But that can't happen. If there are 5 states, you have to be at one of them. So that means any finite state Markov chain has a transient state. And if you can identify that one, then everything that it leads to is also, we'll try it again. Every finite Markov chain has a recurrent state, sorry. If you could find that recurrent state, and then this theorem too tells you that everything that state leads to is also recurrent, that's a tremendous time saver. I'm almost tempted to do problem 1 on the sample test.
Professor,
Yeah.
could I ask if you assigned this problem, I don't know how long ago, but it's problem 18. And it's kind of like what you're talking about right now. It's basically saying that you have like almost in like this infinite like Markov chain, and you have it's a simple Markov chain, so you're only going up 1, and so you have the chance of going up like 1 step is p, but every single I think step has the 1 minus. Sorry, you guys can read the problem.
Yeah, I'm happy to do that. Did I assign that problem? I don't recall right now.
I think so. I'm not sure. I did it, so I
Yeah.
think you did.
Yeah, and we're at a place I think we should be able to do it anyway, and I think it's on the sample test. Okay. So,
Okay.
So why don't we take a few minutes and do it? So let me flip the page and just do that problem. So add the page, put some lines on the new page and get the pictures up here. So let's look at 18 from the book. But you could also check the sample test. I think it's problem, I don't know, 4, 5, or 6, one of those on the sample test. So it says we have a Markov chain on non-negative integers. Non-negative means you start at 0 and 1 and 2 and 3, you go on from there. So this is an infinite Markov chain. It never stops. And such that starting at x, the chain goes to state x plus 1 with probability p. So whatever x is, the probability of going up is p. And that goes on. And p is a probability between 0 and 1 strictly. And it goes to 0 with probability 1 minus p. The chance of going down here is 1 minus p. And so forth. Now, by the way, sometimes a chain like this has nice descriptive names. It's called a birth disaster chain, because you're either going up by 1, which you can think of as a birth in terms of the population, or the population is wiped out. Now, the thing that's interesting, even if the population gets wiped out, there's spontaneous generation. You can have a birth out of nothing. So this might lead to a creationist kind of argument that, that even though a species would be eliminated, something supernatural might happen to actually recreate it, or maybe, I don't know, maybe some alien drops an individual into the mix somehow, or organism. Anyway, so it's called a birth catastrophe chain. Or birth disaster chain. Because you're either going up by 1 consistently or going all the way down to 0. Not bad to model what can happen, especially, if you're not very experienced with working on computers and you don't know how to save things, and you do something and then you hit the wrong button and everything collapses, and you don't, all your work is gone forever. That can be modeled by this situation as well. Okay. Show the chain is irreducible. Okay, so what would the chain being irreducible mean? It would mean, so from our definition, the state space is what? 0, 1, 2, 3, etc. All the integers and 0. And it's irreducible if what? You pick 2 states in here. The probability, well, I think it would be easiest just to put in terms of that. Irreducible means I communicates with J, and J communicates with I, for all I and J where in S. I think that's pretty easy to see, because let's just take an example. Suppose I took I to be 1, and I pick J to be 6. I need 1 and 6 to communicate, but 1 communicating with 6 means what? 1 leads to 6 and 6 leads to 1. It's pretty clear that if you're at 1, you should be able to get up to 6 with positive probability, because 6 is over here. 4, 5, and 6. And it's clear that if you want to go from 1 to 6, you could just go up by 1 step at a time. So there is a positive way to get from 1 to 6. A positive way meaning there's a positive probability, which is p to the 5th. Is that right? 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4, 5. Yeah, p to the 5th. So it's pretty clear there'd be a positive way of going from 1 to 6. And if you want to get from 6 to 1, the only way to do it is you're going to have to eventually have a catastrophe. It could happen right at 6, or you can go up higher and then have it. No matter where it happens, you have to have one of these catastrophes occur, which has probability 1 minus p. And then from there, the only thing that could happen is going up by 1, and so you get to 1. So it's clear that you can get from 6 to 1 eventually. So that kind of argument would show that it's irreducible. I'm trying to say that no matter what I and j you choose here, there's a positive probability. Suppose I is the smaller number of going from I to j directly, just straight up motion. And if j is the bigger number, if in order to get from j to I, you're going to have to eventually have a catastrophe and then work yourself up to I again. So that says it is irreducible. That's part A. Part B. Find the probability if you start at 0, that at time 0, you're back to n. So part B, was find if you start at 0, the time that your first step to 0 is in units. I think that's what they're asking us to find. And they want us to do that whenever n is greater than or equal to 1. I would rewrite what this means. When they use the subscript, we've already seen that that means you want to first be at 0 in units, knowing that you started at 0 times 0. Now let me see, am I doing that right? How's my notation for my x's? Do I need a subscript notation? I'm trying to remember.
I think that's right. But that's how I wrote it out.
Yeah, let me double check. Something's bothering me a little bit. I can just go back and see how I write this. Yeah, they don't use this though, do they? Isn't our notation this? Time 0, your state 0. I don't think it's parentheses. Because I think we have, we are at time 0, time 1. I think this is what we're using for the state at that particular time. And of course, this is more confusing in a way, but I mean, there's two things here. This is the time and this is the state. And they're both zeros, but they're different zeros, right? This is where you are at time 0, and this is the state 0. Okay, so I think this is what we're trying to figure out, and this is saying, oh, n had to be bigger than 1, that's fine. So we're saying the first time that we return to 0 would be 1, 2, etc. Okay. So what do we know? We know we're starting at 0. So our starting point on the diagram is here. And we start there at time 0. And what do we want to find? The probability that the first time we'll return is n to 0 is n steps later. So let's just do an example to get the idea. Suppose n is equal to 3. So then we'd be trying to find the chance that you first get back to 0 in 3 steps, given that you started at time 0 at state 0. But that's pretty clear. So if you're here and you want to first get back in 3 steps, you have to go up again, and then down, right? You can't go up and then down because then you're already back in 2 steps. Remember, the hitting time is the first time you get back. So the first time you get back to 0 is 3 steps. The only way to do that on this diagram would be to go up once, twice, and then have a catastrophe. So I'm suggesting this one would be what? P squared times 1 minus P. And if that makes sense to you, then I think we can do the more general one. The first time you get back to 0 is n steps. So you'd have to have n minus steps up, n minus 1 steps up. And then the catastrophe step, right? So if you're starting at 0 and you want to first get back to here in n steps, you'd have to go n minus 1 steps up, and then the catastrophe step all the way back to 0. That's the only way you can first get back in n steps. Does that make sense? So I'm saying this is this. And an example which sort of led me to this was this case. There's nothing wrong with doing a numerical example to see how things go. Okay, we're done with B. Let's see. Show that the chain is recurrent. Okay, so I haven't defined what it means for a chain to be recurrent, but it's easy to do. The chain is recurrent if all the states in the chain are recurrent. Okay, so we know what it means for a particular state to be recurrent. A particular state is recurrent if what? Rho I equals 1. That's a particular state I. If this is true for all I in S, then we say the chain is recurrent. So they're saying in part C that no matter what state we are, it's recurrent. The chance of getting back from any state to itself eventually will be 1. Well, okay. I'm not sure how clear that is, and so I think they say show it. Why don't we start off with I0, I'm sorry, rho 0, 0. So that's, what does that mean? If you start off at time 0 at state 0, what's the probability time to get back to 0 is finite, right? Okay. So, but that would be we've done this before. The time it takes to first get back to 0 could be 1, given that we started at time 0 at 0. Or the probability of the time we first get back to 0 is 2, given we started off. I need the parentheses here, sorry. 0. And so on. I'll do one more and then do 3 dots. Time first get back to 0 is 3 units of time. Given that it's 0, you're at 0. And more. Okay. But we can do this because we have a formula for this. Given you started at 0, given you started at 0, the time it takes to first get back is this. So in this case, when the time is 1, that would just be a loop here. Is there a loop here? Yeah, I guess I don't have the diagram right, do I? Isn't there a loop at 0? I think I left something out. Let me see if I did do that. Because the chance from any state to go anywhere must be 1. It's either up or down, that's all fine. Here it should be up or down. So the chance, there's a loop up here, I think. So I think my diagram was incomplete. Because at 0, what happens? Either you go up with probability p to 1 or you don't. It's almost like you're at 0 and you have another catastrophe, you stay at 0. And you just don't advance. Okay. So I think that's how the picture should have looked. So what does this all look like? If you're at 0, and the first time you return to 0 is 1 step, the probability of that would be the 1 minus p. That would be the loop here. Okay, so this one would be the 1 minus p. What's the next one? If you're at 0 and you want to first come back to 0 in 2 steps, then what did you have to do? You had to go up 1 and then go back. So that would have been p times 1 minus p. What about this one? You started at 0 and you want to first get back in 3 steps. You can't loop there because you would have gotten back too soon. So you have to go up, and then get back. If you went up and down, you're back before 3 steps. That's no good. So you really want to go up, and then down. So the next one would be this. P twice and then 1 minus p. So we can see what we're doing now. We're adding up the series that looks like 1 minus p, 1 minus p times, p times 1 minus p. 1 is p squared times 1 minus p. And so on. And when you do all of that, that's row 0, 0. Okay, so what could you do? You could factor out the 1 minus p. P when you do that, you have 1 plus p squared plus dot, dot, dot. But that's a geometric series. sum of the geometric series is a over 1 minus p in this case. So it'd be 1 minus p, and that's times 1 minus c. And that's 1. So that's showing that 0. So what have we shown? We've shown 0 is recurrent. Why? Because that's the definition of recurrent. 0, 0 is 1. But I needed to know the formula for the geometric series. This would be I'm using the geometric series formula. It's okay as long as p is strictly between 1 and 0, right? Which I think they told you to assume that to begin with. Yep. Okay, now from here, there's 2 ways to go. One way would be to use our theorem. 0 is recurrent, right? But 0 leads to 1. Why? There's a positive probability of going from 0 to 1. All I have to do is go up a step with probability p. 0 is recurrent. It leads to 1 by the theorem 2 that we did the explanation for in class. That means what? 1 is recurrent. And the probability of eventually going from 0 to 1 is 1. But really all we want is 1 to be recurrent here. So that follows by theorem 2. So now we know 0 and 1 are recurrent. What about 2? Well, 1 leads to 2. 1 we just showed is recurrent. By theorem 2, wherever it leads to is also recurrent. So 2 is recurrent. Keep doing that over and over. So 2 is recurrent. 2 leads to 3. Therefore, by the theorem, 3 is recurrent, etc. You can keep going forever. That's the nice way to do it, using the theorem 2 that we explained in class today. If you didn't want to use theorem 2, could you do it straight from definition? Probably. Probably I'll need the geometric series again. Let's see how that would work. If instead of reusing the theorem, if you wanted just to do it directly, then what does this mean? It's the probability that the first time you're at 1, well, is finite, given that you started where? At 1? Yeah, so given that you started at 1, what's the chance, the probability that you get back in a finite amount of time? And we're trying to show, well, this is the definition of row 1, 1. And we're trying to show that this equals 1. And we're trying not to use the theorem. The theorem is the easiest way to do it. Okay, but if you did it just the way we did 0, 0, this would be the probability that the time at first to get to 1 is 1, unit of time starting at 1, plus the probability of the time it takes to first get to 1 is 2 units of time, given that you started at 1, plus the probability that the time it takes to get to 1 is first to get to 1 is 3 units of time, given that you started at time 1, etc. Okay, now I don't think we did this. We just did 0 to something. So we don't know these guys. Well, we don't know them, but we can figure them out. So this is a lot more roundabout way, but it still should be doable. Given that you started at 1, what's the chance that you first get back to 1 in 1 unit of time? Go back to the picture. If you're here, you can't get back to one in 1 unit at a time. Why? You either go down or you go up. You're not back at one. So that can't even occur. So the first term here is 0. What's the chance that the first time to get back to 1 is 2 units of time, given that you started at 1? Given that you started at 1, if you first get back here in 2 units of time, it can happen. The only way it can happen is to go down and then come up, right? So that would be P, 1 minus P times P. Similar to what we did before, but slightly different. So what did I just say? P times 1 minus P? No. Forgot what I said. I want to be at 1 and I want to first get back in 2 units of time. So 1 minus P times P. Down and then up. So 1 minus P times P. That added to this. If I want it, starting at 1, I want to first get back in 3 units of time. Back up to the diagram, see how that's doable. Starting here, want to get back for the first time in 3 units of time. Ah, that's harder. Why? You can do it. You can go up 1, go down, and then go up 1 again. And that would be getting from 1 back to 1 for the first time in 3 units of time. Go up, go down, go up. That'll be P times 1 minus P times P. But unfortunately, that's not the only way. What's the other way? You can go directly down, loop here once, and then go up. Okay, so I'm getting discouraged. I'm not saying it's hard, but it's obviously longer than using the theorem because there are 2 paths here, right? So what were the 2 paths? One was going up, which had another probability of P, then having a catastrophe, and then going up again. However, instead of doing that, you could have had your catastrophe right off the bat and then loop twice at 0. Well, once at 0. Oh. Yeah. 1 minus P is a catastrophe, loop again, and then go up with probability P. Those are the only 2 ways I think are possible to go from where? From 1 back to 1 for the first time in 3 steps. If I go up 2, I have to then go down, and I don't have enough time to get there in 3 steps. So I can go up 1, down, and then up, which I did. Or you can go down immediately and just waste 1 step here and then go up. Okay. I think I'm ready not to go further. Now, maybe I'm quitting it too soon. All right, how about one more term, just to see how bad it gets. You want to first get there in 4 steps, given that you started there in the beginning. Hopefully, there's only 2 possibilities here. I think that may be the case. So if we start here, we want to first get back in 4 steps. We can go up twice, have the catastrophe, and then go up again. So say that again. That would have been up twice. P squared, have the catastrophe, and then up again. That would be one way to go from the state 1 back to 1 for the first time in 4 steps. But are there other ways? Yeah, there are. So the way I just did was what? We're going up twice. Suppose we just went up one time and then came down and then looped one time here and then came over. So that would be P, 1 minus P, another 1 minus P, and then another P. So that would have been P, 1 minus P, another 1 minus P, and then P. Okay, so that would have been a second way. Is there a third way? So starting here, wanting to end up here for the first time in 4 steps. Well, you could have just had a catastrophe from the beginning and then waste 2 steps here and then go over, right? So I guess it breaks down into, you could have gone up to, down here, and then over, up 1, this, and then loop, and then over. And now I'm saying you could have just gone down, loop twice, and then over. So that would be 1 minus P squared times P. That's already discouraging, more discouraging. So the other way of doing this is 1 minus P, loop there, and then P, right? What's discouraging about this? Well, it's looking like here there was no way to do it. Here there's only 1 path to consider. Here there's 2 paths to consider. Here there's 3 paths to consider. So it appears like there's ever more paths to consider. And that's a little discouraging. I'm not saying there isn't a pattern here, but this is just going from 1 to 1. Then we'd have to do 2 to 2 and all the rest. So I think this is a great argument for the theorem. The theorem we did in class, right? Because once you know that 0 is recurrent and 0 leads to 1, then by the theorem 1 is recurrent. And once you know 1 is recurrent and 1 leads to 2, then by the theorem 2 is recurrent. And you can just inductively continue doing that. That looks better and better, as opposed to counting all the ways that paths look. I'm not saying there isn't a pattern here. There probably is. But I don't want to do this over and over again for different, different row IIs. So I think the theorem is probably what they want you to use. Questions? Which is pretty cool now. So what does it mean? It means that every state here is recurrent. So no matter what P, as long as P is between 0 and 1, you're going to return to every state with probability 1. Now I'll warn you, this thing keeps going on forever, right? So when you have Markov chains with an infinite number of states, then the intuition gets a little not quite as sharp. Or, like in calculus, whenever you deal with infinities, usually limits or infinite series or infinite sequences, we have to hone our intuition. It doesn't come naturally. So what I'm saying is, this is one example. It's nice, everything is recurrent here. So if you were to stay at any state here, I mean, it's pretty interesting. It's saying that even if you were to work your way up to 1,000, the chance of going from 1,000 to itself is 1. Even though it took a long time to work yourself up to 1,000. Because if you have a catastrophe, if you count all the ways there are to get back, they all add up to 1. So here's a question. Could there be an infinite chain that's not recurrent? And the answer is yeah. That's sort of where I ended last time on Wednesday. Here's a simple example. 0 to 1, 1 to 2. There was no falling back if it was pure birth. This chain is not recurrent. Why? The chance of getting back to 0 from 0 is 0. You can't even do it in 1 step. You can't do it in 2 steps. Why? There's no way to get back. So this cannot happen. So this is actually 0, not 1. What's the chance of getting from 1 back to 1 eventually? 0. Okay, same thing. I mean, once you're at 1, you leave, you never get back. So you could have infinite chains that are all transient. You can have infinite chains that are all recurrent. And sort of obvious question is, can you have an infinite chain that has both? Yeah, you could. Can you think of one? Can you think of an infinite chain that has both transient and recurrent states? We've got infinite chains that are all transient. This simple example is that. By the way, this simple example would still work even if you threw loops in here, for example, because you're still eventually leaving, and then once you leave, you won't get back. I'm trying to think if there's a nice example. I just pose that out loud. Is there an example of a Markov chain having an infinite number of states where some of the states are transient and some of them are recurrent? Let me help you. Suppose you have this guy, but instead of going up, let's see how I can do this. I'm trying to combine the two just to show you that it's possible. So sure. Let's suppose the even states are like this. And these are all ones. And it continues in that manner. What is that going to mean? States 0, 2, 4, 6, 8, 10, all of these are all going to be transient, right? Because once you leave, you never get back. But suppose Suppose we change these ones to be something else. How about, can we make them all halves? So there's a half chance to go up. But there's a 50% chance to go up. You gotta have some probability of going down or somewhere. Well, let's make them this way. Let's make them going down like this. To where? Maybe the odd states. Okay, so since everything has to add up to 1. That would work. Now let's think about it. Why don't we make this thing the one we just did? So the one we just did had this being what? P, 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 P. Okay, and P forever. And then this was what? 1 minus P, I guess. P is still between what, 0 and 1. So I could pick it to be a half if you want, but it doesn't matter. And then there are these catastrophes. So there's this chance of going down, what, 1 minus P. And this chance of going down would be 1 minus P. And so forth. So what am I doing? I'm trying to glue the two cases that I just showed you together. Etc. Okay. So once you're down here, I think this is the case we just did. So these states are what? Recurrent. Because the chance of going from 1 back to itself is going to be the same as it was before. When we didn't call it 1 before, we called the first state 0, but the picture is really the same as the one we just did. So what am I arguing? I'm arguing all of these are recurrent. And I'm arguing that all of these are what? Transient. And you could see they're transient because the chance of going from many of these numbers back to itself is 0. Once you leave, you never return. You leave 4, you can't get back. If you go down here, you never get anywhere else. And if you go up here, again, there's no way to get back down to 6. So this is just a modified version of this thing. How did I modify it? Instead of just saying 100% you had to go up, I said 50% you went up and 50% you went into this guy.
Professor, I have a question.
Sure.
Is it necessary to have those paths going down for like these statements to be true? Or did you want to just have those paths down to like just keep like both the even the odds somewhat connected?
Oh, I needed them because when I leave a state, it has to add up to 1.
Yeah, but before you had from 0 to 2, you had that probability as just 1. Would it be okay to have like these two, like, I guess, separate like chains where it's like just the odds and just the evens? Or
Yeah, I guess you could. So all right. Yeah. Okay, so yeah, I think that's a nice comment. What you're telling me is I didn't have to make them connect at all. Okay. I have this one sort of filling into here, right?
yeah, but it still would have been correct what you had before, right? You just had like
Yeah.
the ones, and then we just like, oh, these are, if you're even, you'll stay even forever. And if you're odd, there's a chance that you can be any odd number. You'll get to every odd number at some point, right? That's
Yeah.
kind of like,
You're absolutely right. And if you think of it that way, the only idea that one has to come up with is take the two previous cases and instead of making them 0, 1, 2, 3, make one of them even and make one of them odd. So that they don't, you're talking about different states. Yeah. Yeah. So I agree with him. I'm sorry, who am I agreeing with? I don't even see.
as Ricky.
Ricky,
Sorry.
thank you. Yeah, thank you, Ricky. Yeah, so Ricky's saying, I don't have to get this creative. I could have just stuck with this guy here and not have the arrows going down. But have the states be 0, 2, 4, 6, and then just have this below. And then you would have half of the states be what? Transient and the other half be recurrent. So this sort of shows, yeah, thank you. I like your way of doing it too. My way of doing it is well, it's not wrong. It's just more complicated than it need be. And you're pointing out it could be a little simpler. I agree. So you could have let me see. Yeah, I guess that's good enough. All I was trying to say is that you could have an infinite state space. They don't all have to be recurrent and they don't all have to be transient. They could have some mix. And of course, if you did, I've got half of them being transient and the other half being recurrent, right? But you probably could have, you could do this kind of stuff too, right? You could do, let's just do 3, 4, 5, 6, 7. Have these all going up with 1. And just have what, 0, 1, and 2. Just look like this. And these would all be transient again. This goes on forever. And this would be recurrent. So you could have, you could have them, and you could have any number of states being recurrent you want, and any number of the remaining, and all the rest being transient. So I think anything you can dream up is possible in terms of a mix of transient and recurrent. Why did this all come to mind? Because the one they asked us to do was this one, and it's pretty cool that all of these are recurrent. The part that's cool about that is you could start at 1 million. So if you're way to the right, 1 million units to the right here, at some state 1 million, if you start there, the chance of returning there will be 1, even though you can go infinitely far to the right of 1 million, and you can go all the way down to 0. But no matter how far you wander above or below 1 million, eventually you're going to get back with probability 1, which is not, it could very well be thought that, well, yeah, you could think that, what that implies is, since once they're all recurrent, and since there's a way to get from every state to every other state here, that they're all recurrent, so that even if you start as far as away, 2 states too far, have 2 states that are as far as you want from each other, if you're going to play this game long enough, you'll be able to get with probability 1 of getting 1 back to the other, back and forth to the other. Other questions? Is there anything on the sample test that you may just need clarification? In other words, you're not even asking me how to do the problem, just need to know what does it mean or something like that. So if there's a question like that, I'd be happy to help. Because I don't want you to be scratching your head wondering what the question means.
I have a question about the studying. Are you gonna have a study session like you normally do, where we go over the problems on the sample test?
Oh, we will. Oh, no, we will.
Oh, okay.
I don't know when yet. I guess we should have it sooner than later because you picked the dates. What'd you pick?
29.
29th, which is like what, 12 days from now, something like that?
Yeah.
Yeah. So, we're still at the end of the fourth week. So it's Friday and I just gave you the test. So we're not going to do this. Not going to do it.
Yeah.
But sometime next week, we should do it.
Okay. Also, you said you'll give us the cutoff where we're gonna leave off. It's gonna be on the final, right? I mean, on the midterm.
Oh, yeah. Well, I think
Okay.
given that the test is going to be on Wednesday of the 6th week, I think it'll probably be Friday of the 5th week. Whatever we cover next week will be okay. But whatever we cover Monday, I wouldn't give you on Wednesday. So if you want, I don't know how far I'm going to get in the next week. But we have, we have all of next week, and then we have to Wednesday the day after. So probably everything I cover up until Friday of next, a week from today.
Okay. Thank you.
Sure. Anyone need clarification on any, what problems mean? If you have that, this is a good time to ask me about it. Okay, well, I think I'll turn you loose. Weekend, almost. Well, I don't know if you may have other classes, I do. But it's getting close.
Thanks,
And
Professor.
yeah,
Thank you.
yeah, you're very welcome. Thanks for hanging with me here. So I will close this out.